We're going to be covering the central limit theorem in section 6.4. And basically what this allows us to do is use a normal distribution for some very meaningful and important applications. We're going to talk about it, the notation, applying it, and introduce hypothesis testing, and we won't go too far into the correction for a finite population, but I will show you that. So the central limit theorem, it says for all samples of the same size n, as long as n is greater than 30, so our sample size is larger than 30, the sampling distribution of the mean can be approximated by a normal distribution with a mean of mu and a standard deviation of sigma divided by the square root of n. And we'll go into that a little bit more. But basically what it's saying is that we can take data like 6.21 and approximately normalize it and turn it into 6.22. This is the central limit theorem. I encourage you to kind of stop and look at this for a moment. So basically what it's saying is we're given some sort of population with this information and simple random samples all of the same size n. So we want to ask ourselves the requirement. So the first thing we say, like, is it normal? We can use this if it's normal. And that comes from right here. We're checking the requirements. Is the distribution normal? Or is the sample size greater than 30? If we meet these two criteria, we can then move on here to applying the central limit theorem. And how we're going to apply it is, actually this slide here is better. So again, we're going to check the requirements of the data, and then if it's just an individual value of x, we'll just use the methods from 6.2. We'll either use Excel or maybe we'll have to normalize it. If they just want the z-score, we could just normalize it there. But if we are asked to find the mean, or x bar, from a sample of n, so the average of averages, we will use the same mean. The mean is the same, but we'll have to change our standard deviation to be the standard deviation of the population divided by the square root of n, the number of trials. And all that comes from here. Oops, let me just x bar. All that comes from here, but this is the main practical way that we'll be using this. And again, this is just repeating what we already said. If we are trying to find the mean of a sample, we can use the same mean, but we do have to change the standard deviation. So in this example, an elevator car has a placard stating the maximum capacity is 4,000 pounds, 27 passengers. This converts to a mean weight of 148, so they give us the mean, when the elevator is full. We will assume a worst case scenario in which the elevator is filled with 27 adult males. Assume that an adult male has a weight that is normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. Find the probability that one randomly selected adult male has a weight greater than 148. Find the probability that a sample of 27 randomly selected adult males has a mean weight. So we're doing two different things here. Let's look at A. So if we're just finding the probability of one randomly selected adult male, well, let's just make sure, is this normally distributed or is our n greater than 30? So it says here that it's normally distributed, so we can go ahead and just use Excel like we have been. So we're trying to find out the probability that this is greater than 148. So let's draw. And they give us our adult mean is 189. And so 148 is over here, and we want greater than. Now remember that Excel is going to give us this value to the left, but let's go ahead and type that in. And if you forget how to use this, just go back to section 6.2 to recall how to type these in. So, oops, we want the x value. I'm sorry, we want the probability. We know the x value. Our mean is 189. Our standard deviation is 39. And so we get 0.1466. So the probability here is 1 minus 0.1466. When we calculate that, we get, 0.8534. So 0.8534. So the probability that one randomly selected adult male has a weight greater than 148 is about 85%. So find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148. Why are we talking about 148? Because that's what the elevator used to determine there. So, all right, we're not finding a single value. We're finding a sample of 27. So either it needs to be normally distributed or the sample needs to be bigger than 30. Well, it's not bigger than 30, but it is normally distributed, so we can use the central limit theorem. However, we have to say, okay, the mu of this is equal to the original, but the standard deviation of this sample is this formula here. So that would be 39 divided by the square root of 27. And that's going to give us 7.51. So again, here we've got our mean of the sample mean as 189. And we're still trying to find 148, which is our mean here of this sample. We want to know the greater than. So when we type it in, it's not going to be the same as before because the standard deviation changed. So what is the likelihood here? So the x we're talking about is 148. The mean is 189. But now it's 7.51. So what is the probability? That means it's really, really, really small. That's essentially 0. So we could say that this space here is essentially like 0, and then so this would be about 0.99. We don't want to say 1 because it's not certain. That's not actually 0, but it's like 0.00000, so it's 0.99999. So what is the probability? Almost certain, 99% that they're going to have a mean weight greater than 148. So again, you can kind of think of this here. It's going to be overweight if it's filled with 27 randomly selected adult males. That can be, it's a pretty safe, 0.99999 assumption, almost certain. So go ahead and give these a try. And we're just going to introduce hypothesis testing. Oops, did I skip over that? Sorry, y'all. There's the answers. So again, we're going to be talking about significantly less than or significantly greater than. Assume that a population of human body temperatures has a mean of 98.6, that's what we always talk about, and that the population standard deviation is 0.62. If a sample size of n equals 106 is randomly selected, find the probability of getting a mean of 98.2 or lower. All right, so we're talking about a sample size and a mean, and because the n is greater than 30, we can apply the central limit theorem here. So we know that the mu of this is going to stay the same, but we need to adjust our standard deviation. So that's going to be 0.62 divided by the square root of 106, and I get 0.06. So essentially what we're trying to find out here, so we've got our is 98.6, and we want to find the probability of getting a mean of 98.2, so seems like it'd be like right there maybe, or lower. Mean of 98.2. Remember, we're not finding the single value, we're finding the value of the mean. So let's use Excel. And we are looking for the probability. We have 98.2, our mean of 98.6, our standard deviation of 0.06, and we get essentially 0 again. This value is 0. So this is 0.999999. So what's the probability? Essentially, the probability that you're going to get a mean of 98.2 or lower is certain, 99%. So what does that mean? It might mean that 98.6 is not actually our body temperature. Our body temperature might actually be 98.2. And go ahead and give this one a try. And there you go. We're not going to be using this, but I will leave this here for you to read. We won't be using this, so you don't need to worry about it too much. But this is a correction when we're dealing with a finite population. And that concludes section 6.4.